Examples of power distribution in cylindrical bodies. Though there are complicated analytical formula for current and power distribution in cylinders, a modern way is to use computer simulation. Power density, red lines, and flux density, green arrows, distributions in a cylinder. To the left, we see a non-magnetic part where delta is the reference depth. To the right, we see magnetic steel at the end of surface hardening when the outer layer loses magnetic properties. H is the austenitized layer that will be hardened after quenching. Power and flux density distributions in a tube. To the left, we have a case of low frequency where the wall thickness is much less than the reference depth. Magnetic field penetrates inside the tube. To the right, we have a case of high frequency, where the wall is thicker than reference depth. Distribution is the same as in solid cylinder. Reference depth for different materials and frequencies. Reference depth is a unit of length that may be used for evaluation of electromagnetic processes in conductive bodies, such as coil copper, heated parts, structural components, etc. For through or mass heating, one needs to compare part diameter and delta. If diameter of the body is smaller than reference depth, power absorption is poor and heating efficiency is low. The body is transparent to magnetic field. For surface hardening, we need to compare desired case depth and delta to evaluate if the frequency was selected properly. It is a common practice to use logarithmic scales to cover wide ranges of frequency and delta variation. Power absorbed by workpiece. For parts of a simple shape, flat or cylindrical, placed in uniform magnetic field, absorbed power may be calculated analytically. Power absorbed by the workpiece is equal to resistivity divided by reference depth multiplied by the workpiece surface area and magnetic field squared. Power transfer factor K accounts for the part geometry, material properties, and frequency. In many cases, such as through heating of long parts, this approach is quite accurate. It also gives a clear understanding of relations between power, frequency, and part properties. For real cases with non-uniform magnetic field and complicated part shape, only computer simulation can provide accurate results. Power transfer factor for plate and cylinder. When part thickness or diameter is small, or frequency is low, electrical dimensions are small and K is small also. It is said that the body is transparent for magnetic field at this frequency. Components of induction system or machine that must not be heated by induction, such as fixtures, fasteners, etc., must be transparent. If size of body or frequency are big, K always tends to threshold value K equals 1. For cylinders, there is no maximum of K and electrical efficiency grows with frequency. For plates, there is a small maximum when its thickness equals to 3 reference depths, more exactly 3.14 delta.